My name is Steven Luscher, and I work on the Instagram team at the Facebook offices in California. And I have the good fortune of working with those folks. It's a very, very small team, and we work at problems at a reasonably large scale, at least for how small the team is. And so that I know that when I push a feature or a bug to production, it's going to affect millions of people right away. And that's a responsibility that I take very seriously. And as such, there's something that's been on my mind lately that I wanted to talk to you guys about. It's one of my central concerns these days, and it's the complexity of the user interface code that I'm writing and reading. That's my job. I didn't mention I'm a front-end engineer, so I deal with UI code all day, every day. And a little story. When I joined Instagram, there was this 22-year-old intern wizard who had just spent his summer building a whole swath of new functionality, leaving tons and tons of code behind when he had to go back to school. And I had the bad fortune of sort of passing him in the night. I joined roughly around September when school was starting again. And so he took all of that knowledge out the door with him and left me with all of this code that now was immediately my responsibility to understand, to further, to support, to onboard others with, and to fix, and in some cases to ship, because it was almost there but not quite. So I want that code to be exactly as complex as it needs to be, and not one bit more. That's where my head's at. And we've all felt this, right? We've all been airdropped into a situation or taken a new job, and you get that first bug, and the first bug says, fix something in here, and you go find it, and you open that source file, and maybe it looks something like this, and your job is to understand what's going on here. So what's going on here? I see a lot of branches, if, else, returning, testing some stuff. Things are on fire, 99 problems, and something about badgers. So this code is complex. It has complexity. We can speak about it in terms of its complexity or its simplicity. But how complex is it? That's a question I want to know. Why is it complex, and how can we make it more simple? These are sort of the three things I want to talk about today. So how do we measure complexity? Why are things complex? Well, maybe one useful thing we can do is we can take out all the code and just look at the braces. This is where your code starts to branch, right? This is where the decisions are made, and different paths are taken through this code. So 2, 4, 6, 8, 10, 14 braces in this particular piece of code. I don't know, is that a good measure of complexity? There's this concept of cyclomatic complexity, which is defined as the number of linearly independent paths through a piece of code. So maybe that could be of use to us. Complexity, there are other measures of complexity, right? When we talk about algorithmic complexity, we talk about the big O notation. It's useful for classifying algorithms in terms of how they behave given some change in input. What's the response when you change n? If the amount of time that it takes to process n things increases linearly as you increase the number of things n, then we say an algorithm is O(n) time complex. Or if the amount of memory increases linearly, we say it's O(n) space complex, and these kinds of things. So those are two measures available to us for complexity just in general. But this is a talk about development complexity, how complex it is to read and write user interface code. And specifically as it pertains to human beings building that user interface code, not algorithms processing some items. And I have an intuition that the answer for me is probably going to be in this direction. I'm probably going to want to keep complexity down. It's going to be a good thing. But why is this a good thing? And I think the reason that this is a good thing for me has to do with my limits as a person. Because ultimately, developers are people, and we have limits. Gosh darn it. We have sayings in our language, such as, I'm running up against a wall, or you pushed me over the edge. And these all speak to our limits as human beings, right? Limits like our working memory is sort of finite. The number of things we can juggle in our head at one time. If you read various studies, they'll sort of point to this magic number 7. You can remember the order of 7 digits in a phone number, these kinds of things. And when you start to increase the cognitive load on your working memory, you can sort of enter a saturation state where you're just overwhelmed. And in that saturation state, you can start, like any network, you can start to drop packets. You can start to drop mental packets. You can start to make errors. Speaking of dropping things, if I may, by way of analogy, this gentleman, Jack Calvin, is writing papers on human limits as they relate to juggling, like actually juggling objects, at juggling.org/papers. I love that URL. Highly academic papers on juggling. And if I may, from the conclusion of the human limits of juggling paper, he says, suppose one hand makes a slightly high throw followed by a slightly low throw, such that 2 balls come down at roughly the same time. If a throw has to be made in half the normal time, this requires 4 times the vertical acceleration on behalf of the juggler, on the part of the juggler. And if you're juggling 7 balls, this correction's probably beyond human capabilities. This is all by way of saying that when you're overextended as a developer, you're one high throw away from pushing a bug to production that ruins everything. You're one understeeped cup of tea away from making a critical mistake that just ruins your Friday night. So my goal for this analysis is going to be to keep complexity down in an effort to reduce errors. Or if we invert that, to make things more simple so that we can increase the reliability of our code. And on this, not on this stage, but at this conference in 2011, Rich Hickey, who was the creator of the Clojure programming language, gave a keynote at Strange Loop. It was called Simple Made Easy. Did I get that right? And in that talk, he said, we can only hope to make reliable those things that we can understand. So what device are we going to use? Big O notation, not really applicable here. Cyclomatic complexity, maybe. But I think we need a new notation to talk about the human element here. Talk about the complexity of a program in terms of our limits to be able to understand it completely. So I'd like to propose a more human notation, the big coffee cup N notation. And specifically, this is how much caffeine do I need to feed into my feeble human brain to be able to handle N things at once? Okay, so let's talk about the units on N. N in this case is what? I'm a user interface developer. And if you also work in UI, you know that when you receive a mock from a designer, or if you're whiteboarding a user experience, it typically looks a little bit like this, right? I'm moving from state to state to state of the user interface. So I would like to propose for coffee cup N notation that the units on N is the interface state. And what happens? The question is then, as the number of user interface states increases, what precisely happens to the complexity of our code? All right, let's do an example. So let's say you have a user interface, and it's a notification. There's something in a bar that tells you how many notifications you have. Maybe it's how many emails you have, or how many bugs you need to fix, or how many instant messages, or something. So a notifications widget. And it can be in one of three states. Either you have no notifications, looks something like this. You have somewhere between 1 and 99 notifications, and looks something like that. Or you have more than 99 notifications, everything's on fire, you're drowning. You might as well just go for broke and mark them all as red. So here are our three states. Now, I'm a user interface developer, so my rendering target is the DOM. And the DOM is many things to us. The DOM is it's one element in a layout engine. It's a semantic model of a document. But for this purpose, whatever the DOM means to you, for this talk, I'm going to talk about the DOM as just a way to get stuff in front of your face. It's an object-oriented, stateful API for putting stuff on the screen. And in this way, the DOM is a scene graph, right? And whatever we do to this scene, the DOM remembers what we did, and it keeps a record of this scene over time. And this approach to rendering, it has a name. It's called retained mode rendering. Our UI state in this way is retained in the DOM, and our job as UI developers is to poke and prod at the nodes of the scene graph and perform work on them whenever we want to transition from one state to another state. And we do this by delivering imperatives through the DOM API. Calls like create element, add child, remove child, inner HTML, these kinds of things. So we poke and prod at the DOM to essentially do things like adding, deleting, reordering, and modifying elements of that scene graph. So if I wanted to go from this state to that state, I might issue some imperatives to the DOM saying things like add a badge and then set the badge to 8. Or if I wanted to go from here to here, I'd say add a badge, put some fire on it, and set the badge to read 99 plus. And what's distinctive about this approach is that what we're doing here is we are writing code that models the transitions between states. That's the important piece. We're modeling the transitions between states. So what might this look like in JavaScript? So in JavaScript, I might say if the number of notifications is more than 99, things are on fire. So if we don't already have fire, put it in there. Otherwise, things are probably not on fire anymore. So if we do have fire, back it out, get it out of there. In any case, if the count has fallen to 0, then, and we have a badge on screen, then get it out of there and we're done. If we've reached this line of code, then it must mean we have somewhere in between 1 and 99 notifications. So if we don't already have a badge, put one in there, because we're going to need it for the next step. And the next step is to synthesize some text. If you have more than 99 notifications, I want it to read the string 99 plus. Otherwise, just a string that represents the number of items. And then finally, we got to go get that badge and set its text to whatever that string we synthesized is. How many people have seen code like this in your life? How many people have written code like this in your life? Don't be ashamed. We all have, This is the imperative way. Now, keep your eyes on the next part. This means that for every state n, every possible state n, I could transition to exactly n minus 1 other states, worst case. So in this particular example, or sorry, generally, this means that there are n squared minus n possible transitions given n states in my UI. In this case, 3 states, 3 squared 9 minus 3. I have 6 possible transitions, worst case, that my code needs to model. Now, if someone walked up to my desk and said, you know what, we need a 4th state, and I had to add on Halloween, when you have 31 notifications, I want to change the bell to a pumpkin. I don't know. If someone came to me and added a 4th state, I would have to model, 4 squared 16 minus, I'd have to model 12 transitions. 1 extra state in this world doubles the number of transitions that I have to model. This is bad, because this makes me fearful when someone comes to me with a new product idea or a new state or or something else. It makes me fearful that my code is going to unravel under the pressure of that 1 extra interface state. Because coding interface UI against this model is fundamentally coffee cup n squared minus n. The dominant term is n squared, so this problem is fundamentally quadratic. As the number of states increases, the number of transitions, possible transitions between those states increases quadratically. When the number of states is low, we can keep lids on this, but as the number of states increase, it gets out of hand quickly. So what are we going to do? What are we going to do? I'm hoping that there's another way. Instead of delivering imperatives about what we want to do to the graph to wrestle it into the state that we want it to be in, wouldn't it be nice if we could just make proclamations about what we want the user interface to look like given any input, and it would just be so? Or in another term, what if we could make declarations about what we want the user interface to look like given any input? This right here is a fundamental shift in the way we do user interface programming. It's a shift from the imperative model to the declarative model. And it's a model in which we model the states and not the transitions. So what might this look like if I were to take a stab at that previous example in code? Well, I'd love to be able to do this. I'd love to be able to say, if the number of notifications I have is 0, I want there to be a bell on screen, and I want it to be empty. That's just what I want. I want this to be so. If, on the other hand, it's somewhere in between 1 and 99 things, I want a bell there. I want a badge in it. I want the contents of the badge to be the number of notifications that I have, and that's what I want. Otherwise, things must be on fire because I have more than 99 notifications. So I want a bell that's on fire with a badge in it. I want the badge to just read 99 plus, and I'm out. This is what I want. Now, the astute observer among you will notice that this is not valid JavaScript. So, I can't just expect to write this in console and have it all work. But the good news is that with one small tweak, don't take your eyes off, with one small tweak, really an implementation detail, this right here is valid executable React code today. It's been valid executable React code for a long time. And what React will do with this declarative chunk is every time the state of the world changes, every time the notification count changes, it's going to render, it's going to call this code over and over and over for new advice on what the user interface should look like. And this gives the appearance of user interface programming as sort of an act of issuing drawing commands to a sort of a canvas to re-render the entire UI whenever the data changes. This rendering style also has a name like the last one. It's called immediate mode, in contrast to retained mode rendering. And in this way, you can think of React as an immediate mode abstraction atop the retained mode DOM. We're not going to get away from the DOM being fundamentally a scene graph. But React has built this immediate mode abstraction on top of it. So in terms of complexity, I really like this code because it branches 3 times. It branches once with every state that I have, right? In terms of complexity, the number of branches is sort of equal to the number of possible states. And if that designer comes to me with pumpkin notification state, it's just a matter of adding another if-else case to this branch and telling it what the pumpkins should look like. And the great news about this is that this code is coffee cup n. As the number of states increases, the complexity of the code, in terms of how my feeble brain can understand it, increases linearly. And this is good. I like this a lot. I like working like this very, very much. It's easy to reason. It's easy to read code. It's easy to write code. It's easy to adapt to new requirements and new features. So in review, the place I want to be is I want to model states, not the transitions. I want the framework that I use to allow me to code user interfaces declaratively. And I want to take advantage of this paradigm of immediate mode rendering. Now, this talk could end here. But some of you are thinking, okay, so what? React is not the only declarative user interface framework out there. There are others who use this model. So what makes React any different or any better than anything else? Well, I'd like to say that all of the frameworks that are trying to solve these problems are starting with the same, we start from the same problem. And the problem is that JavaScript is not declarative, fundamentally. So we invent domain-specific languages, which are the parts of speech that allow us to express user interfaces declaratively. We invent these DSLs that sit on a layer atop JavaScript. And we are given parts of speech, sort of like these. To read and write code using these parts of speech requires that we learn something other than JavaScript, right? It's sort of a layer above. And a warning is that anytime you have a domain-specific language, anything that the DSL does not provide for, any parts of speech that are absent, it makes it either really difficult or impossible to express something if you don't have the language to express what you're trying to express. So what's React's DSL? There's a gentleman by the name of Guy Steele. He's a well-respected computer scientist. He's done a lot of documenting of computer languages and designing of computer languages. And he says something that really resonates with me. He says, every programming effort begins with trying to figure out what it is you really want to talk about. I work at a place where we're trying to help capture and share the world's moments. And there's a whole language of photography that goes along with that. There's a whole language of instantaneousness that goes along with that. You think of what you're doing at your jobs, in your startups, in your spare time. What are you trying to achieve? What problem are you trying to solve? You probably have your own whole lexicon that describes those things. you're building your own DSL every time you write a helper function. In fact, Guy says that every time you write a subroutine, you're in effect customizing the base language to be a little bit closer to your domain. Every time I write a function called getPhotos, I'm customizing JavaScript in some way to be a little bit closer to the things that are important to me. So what DSL does React offer? The thing I really, really love about it is that with React, when I'm writing React code, the DSL is up to me. It's up to me to define. And I get to define it using not a limited set of parts of speech, so to speak. I get to define my DSL using the full expressivity of JavaScript. You saw some curly braces on a couple of slides ago. Well, inside React's curly braces, you can write any valid JavaScript expression. Any expression that's valid in JavaScript is valid inside those curly braces in a React render method. And in this way, you can do anything that you can in JavaScript. You can drop a ternary based on some domain-specific language that's close to your problem set. You can use features of the language, such as mapping over arrays. You can use third-party libraries. You see underscore in here, the underscore map function for anyone who's used underscore. And as long React treats your code as a sort of a black box. It doesn't care what happens in there, so long as whatever you return is something that it can render. So long as this code returns something that's renderable, or an array of things that's renderable, or null if you have nothing to render, then the system just works. React doesn't make this decision for your team, what the DSL is going to be in your client code. You do. And this is the thing that I think sets it apart. Other than all of these great things, modeling the states, not the transitions, to keep complexity low, keep errors down, and increase the reliability of our code, being able to program in this declarative style, and being able to take advantage of immediate mode rendering, I think what really sets it apart is that you get to define your own language and your own code on your own terms using the full expressivity of JavaScript. And this is why I've come to love writing user interfaces in React, and my hope is that you will too. So thank you very much for coming, and I hope you enjoy the rest of the show.